Imagine for a second that you have some number here, some creature such that when you take the nth root, and let there be no doubt about it, this is the same thing as the nth root of x. When you take the nth root, you get something approximately equal to 2/3. Well, if the nth root of, if the nth root of x is approximately equal to 2/3, well, if I take both sides and I raise them to the nth power, I would get something like this. I would get a conclusion that says, roughly speaking, that x must be approximately 2/3 raised to the n. And so this thing behaves like powers of 2/3 whenever that happens. That's going to be the key observation to sniff out series that, even though they're not geometric, they may behave somewhat like geometric. We're going to check out the nth root. If the nth root is a constant, winner, winner, chicken dinner, we got ourselves some fairy blood. Okay? That's going to be the sniff test. Alright, so let's do it. So let's formally write that down. Formally, we would say something like this. Yeah, it could be anything. It doesn't have to be 2/3. It could be any kind of stuff. If the triangle raised, if the limit of the triangle raised to the n is equal to the square. Sorry, I'm not sure if I said that right. If the limit of triangle to the 1/nth root is equal to square, then that must imply that the triangle was approximately equal to the square raised to the nth power. At least for large n's, that must be the case. And so this reveals that this sequence, the triangle, behaves roughly like a geometric series. Okay, that's going to be the crucial test right here. We take the nth root and see if it's some constant. All right. That takes us to the next slide. So here are the conditions. We're going to check to see. We're going to check on any sequence. We'll check the nth root. If that gives you some constant r, we throw away the case when r is equal to 1. If r is equal to 1, well, things get a little bit more complicated, because if you remember, those sums we were doing were r to the whatever p plus 1 minus 1 all over r minus 1. That's what the sum of the first p powers of r is equal to. Well, what if r is equal to 1? If r is equal to 1, you get 1 minus 1 over 1 minus 1, which is 0 over 0, which is, of course, one of the famous indeterminate forms. So nothing is confirmed when r is equal to 1. The test is inconclusive. If you get r equals 1, you need to go on to another test. This is no fairyland if r is equal to 1. Alright, so these are the conditions formally. If your nth root is equal to r and your r is not equal to 1, boom, we got ourselves something good. We got some fairy blood in the house. And you can say that the sequence, your series behaves just like a geometric series, where your limit r is the ratio used in the geometric sum. That's right here. Right here, this is a crucial part. So it's going to be really easy. All we do is take the nth root, figure out what that limit is equal to, check that it's not equal to 1. Boom, these two behave the same. This is a close relative of the geometric series, with r being that limit. Okay, talk is cheap. Let's actually do one silly little example and see how that goes. So we check this example. Because of that n, it makes it... Let me see if I can get that onto the screen without white lines. So because of that n right there, it makes it not geometric. But it has some geometric tendencies, as you can see. If without that, it would be a straight out geometric one. So we're going to go through our checklist here. We're going to check that the limit is equal to some r, and we're going to check that r is not equal to 1. And if that happens, yippee-ki-yay, we'll have ourselves a fairy cousin. Okay? Alright, let's do it. Talk is cheap. The absolute value here is really unnecessary because all these things are positive. If they weren't, I would use it. So I'm going to take the limit as n goes towards infinity of n times 2 to the n over 7. There should be a better way to do that. Over 7. And I'm going to take the nth root of that, and I'll check the limit. So this becomes n to the 1 over n times 2 all over 7. I'm distributing this exponent using my excellent algebra skills. And so I'm left with, well, this piece is just a constant. I'm not even worried about that one. I'm left with this piece. For that, maybe I need more room here. The limit as n goes towards infinity. I think I'm going to go with a little thinner. That would give you n, 1 over n would give you, if you try the plug-in method, I reckon that would be infinity to the 0, which is one of the famous indeterminate forms. So of course we can do a little rewrite in L'Hopital, E, L, N, n to the 1 over n. These two cancel, so I'm left with the same thing. Of course I've got a limit as n is running towards infinity. This becomes, I can bring this down, so it becomes E. I can bring the limit up there so long as the function is continuous there. Ln of n, so as n runs towards infinity. So I can work with this limit over here. Let's make it white here, so to indicate that we're just working on this piece right here. That limit will be equal to, as n runs towards infinity, ln of n all over n. I try the plug-in method. Of course I get infinity over infinity, which is perfect because then I can use L'Hopital. That would give me the limit as n goes towards infinity. The derivative of the top, 1 over n. The derivative of the bottom is 1, so that gives me 1 over n. As I plug it in there, I get 1 over infinity, which is equal to 0. So that number over there was equal to 0. So then my limit, I switch back, was equal to e to the 0, which is equal to 1. Aha, so after all that, I get that this limit is equal to 1 times 2 over 7. Yippee-ki-yay. That tells me that it's this guy right here is equal to 2 sevenths. And of course 2 sevenths is not 1, so I check that, I check that. These are the two things I gotta check, and then I can declare that this one, let me see if I got it on the next screen. I've already set it up. I'm that good. So then we can declare, let's see if I did. Maybe I didn't. Haha. So then I can declare that because this was turned out to be 2 sevenths, I can declare that the original series, the one I was trying to figure out, is really a close relative of this one, 2 sevenths. And so then this is geometric, and of course the 2 sevenths is smaller than 1, therefore that converges, and we're done. This was we can say that the original series converges by the ratio test. Oh, sorry, the root test, the nth root test, and we're done. Huh? Not bad. That's the main idea. Come back for some nice examples. We'll see you guys here next time. Paz.